Okay students, now let's go into chapter 6.1 Dynamic Equilibrium. Before we start, let's see the contents in 6.1 Dynamic Equilibrium. The objective of the lesson. At the end of the lesson, students should be able to, in 6.1a, to explain the following terms. We have reversible reaction, dynamic equilibrium, and law of mass action. In Objective 6.1b, at the end of the lesson, students should be able to state the characteristics of a system in an equilibrium system. And lastly, 6.1 Part C, at the end of the lesson, students should be able to interpret the curve of concentration, reactants and products against time for a reversible reaction. Okay, what is reversible reaction? Most chemical reactions are reversible. In many chemical reactions around us, they are reversible at least to some extent. So, what is the definition to a reversible reaction? Reversible reaction which take place in both forward and reverse direction. If we look at the example in the yellow box here, the forward reaction is the reaction forming the product B here, and the reverse reaction is a reaction forming the reactant A here. So, what about a reversible reaction? Firstly, it has a forward reaction, which is the reaction will proceed from left to right. For example, the example below there, the reaction will proceed and indicated by the black arrow down there. And secondly, it has a reverse reaction, which is a reaction will proceed from right to left, and it indicated by the black arrow down there. The reaction proceeds from right to left. And the reversible arrow is indicated by the black arrow down there. The symbol indicates a reversible reaction. For example, we look at an example below. The example below. In a reversible reaction, initially the reaction proceeds toward the formation of product. Look at the arrow down there. Firstly, the reaction will proceed to form 2SO3. In a reversible reaction, initially the reaction proceeds toward the formation of the product. We can look at an example below. Initially, the reaction will produce 2SO3. As soon as some product's molecule form, the reverse process begins to take place. Let's take your attention to the example below. Reactant molecules are formed from the product molecule. Now comes the reverse arrow in the reaction. And now the reaction had completed as a reversible reaction. So this is the end of the first definition, which is the reversible reaction. Let's take you to the objective slide. Next, we go to next objective 6.1a, explain the terms part 2, the dynamic equilibrium. So, What is dynamic equilibrium? The system reaches an equilibrium when, firstly, a forward and a reverse reaction proceed at an equal rate, and secondly, the concentrations of reactants and products remain the same or remain constant over time. So there are two factors that will tell you whether the system reached an equilibrium or not. When a chemical system is at equilibrium, there are no visible changes to the system. The concentrations of every substance in the reaction will remain constant at an equilibrium. So when these two factors are obeyed in a reversible reaction, the system is said to be in a dynamic equilibrium. Let's look at an example here. In a dynamic equilibrium, what happened in the reaction? For example, we have a mixture of water molecules and dye molecules. Firstly, there are crystal of dye is placed in the water. The dye crystal are concentrated in one area here. When the reaction, the dye dissolve in the water and a net movement of dye molecule occur. We can look at there are movement of dye molecule here. A net movement of water molecules occur in opposite direction. It means the water molecule and the dye molecule are moving in opposite direction and bouncing to each other. After some equilibrium reach, equal distribution of molecule results, which means the dye in the water already diffuse, the dye molecule already diffuse in the water molecule. Eventually, the water and the dye molecule are equally distributed throughout the container. So this is what happened in a reaction, in a dynamic equilibrium reaction. Objective 6.1a, Part 3, the definition to law of mass action. The equilibrium concentration of reactants and product are related by law of mass action, or it is also known as law of chemical equilibrium. Do you know what is law of chemical equilibrium or law of mass action? At a given temperature, a chemical system reaches a state which the particular ratio of the reactant and product concentrations has a constant value. For a particular system and temperature, the same equilibrium state is attained regardless of how the reaction is run. It means regardless how we do the reaction, the same equilibrium will be attained. From the definition of law of chemical equilibrium, we can consider the definition, we can write the definition in the form of simple formula. For example, we have this reaction. Consider the general reaction equation. We have reactant A and B. We have reactant A and B, and the reaction produce products C and D. At equilibrium, based on law of chemical equilibrium, the ratio of the products over the ratio of the concentration of the products over concentration of reactants, we produce a constant. We call it equilibrium constant, and it is indicated by the letter capital K. The small letter A, B, C, and D are the stoichiometric coefficients for the reactant species. The reacting species, the capital letter A, B, C, and D. And to write the law of chemical equilibrium, we will write it as concentration of product. The concentration is indicated by the square bracket here. Raised to the power of its stoichiometric coefficient. For example, the product C. Concentration of product C raised to the power of its stoichiometric coefficient. Its stoichiometric coefficient is small c. Times by concentration of the product D raised to the power of its stoichiometric coefficient, the small d. The concentration of products ratio to the concentration of the reactants. If we look at the equation, our reactants are A and B. So we have concentration of capital A raised to the power of its stoichiometric coefficient, the small a here, raised to the power of small letter A, times we have reactant B. Concentration of reactant B raised to the power of its stoichiometric coefficient. We have small letter b here. The power is raised to the small letter b here. And everything is equal to the equilibrium constant. We indicate it as capital letter K, the equilibrium constant. So it is the end of the definition to the law of chemical equilibrium. In the previous slide, we had looked at the definition and the formula for law of mass action, or also known as law of mass equilibrium. So students, let's recap by doing this exercise. It's time to take your pen and paper to do the exercise. Enjoy your exercise. So, are you ready with the answer? Firstly, the equilibrium constant is indicated by the capital letter K here. Why I use the small c below? Because of the phases of the components, the reactants and the products are in form of gases. And gases, it has its own concentration. So C here representing the concentration of gases. So equilibrium constants, we start with capital K equal to, by definition to the law of chemical equilibrium or law of mass action, mass equilibrium, the ratio of the products raised to the power of its coefficient over the concentration of the reactants raised to the power of its coefficient. So let's look at how to do this exercise. Now our product is here, CH3OH. So let's put it in the form of concentration, the square bracket. Concentration of CH3OH. We only have one product, so directly to over. Now we look at the reactants. We have two reactants here. The first one is CO. So let's put it as concentration of CO. We have another reactant which is H2. So let's put it in a form of concentration H2, and please note we have the coefficient 2 here and it belongs to the power of H2. So the equilibrium equation for this reaction is Kc equals to concentration of CH3OH over concentration of CO times concentration of H2 raised to the power of 2. Objective 6.1b, state the characteristics of a system in an equilibrium. Okay students, now we go to the next slide, which is the characteristics of a system in equilibrium. I will show you there are 4 characteristics of a system in equilibrium. The first one, the equilibrium can be approached from the forward or reverse direction, and the final equilibrium position will be the same. The second characteristic is the rate of forward reaction will be equal to the rate of reverse reaction. The third one, the reaction must be in a closed system. It means nothing else can disturb the equilibrium reaction. And the last one, the fourth one, the properties such as concentrations of reactants and products, pressure, and color are constant throughout the equilibrium reaction. So these are 4 characteristics of a system in equilibrium. Once these 4 characteristics are achieved in a reaction, then we can say that the reaction is in equilibrium. So it comes to the end of my slide. The last part in 6.1 dynamic equilibrium, objective 6.1c, interpret the curve of concentration reactants and products against time for a reversible reaction. An equilibrium reaction can be interpreted into concentration against time graph. Let's look at the graph. Let's focus on the graph. Check the y-axis. The y-axis as concentration and the x-axis as time. Concentration against time graph. As the reaction proceeds, or we look at the increase in time, increase in the x-axis, concentration of product will increase. Here, concentration of product will increase, and at some point, when the equilibrium achieved, the concentration remain constant or unchanged. So from this graph, for a reaction A plus B forming product C and D, the concentration of C and D increase with increasing in time, indicated by this graph, this line, the red line and the black line. And as the time increase, as the reaction proceeds, what will happen to the product A and B, the concentration of the product A and B will decrease. So it's what happened in a reaction. Up to a point TA, or at a time when the equilibrium achieved, both reaction has no further change in the concentration. We look at the concentration here, it's constant. It will give one value here, and the same as the reactant, the concentration will give one value here. So at equilibrium, the concentration of products or reactant has no further change anymore. It becomes constant. So at this point, we say that the system is in the state of equilibrium. The system had reached equilibrium at time TA. So this is how the concentration against time graph works to explain the equilibrium in the reaction. We already looked at in the previous slide that there are 2 points that we can use to say whether the reversible reaction achieve equilibrium or not. The first point is the concentration of reactants and products remain the same once the reaction achieve equilibrium. The second point is in a reversible reaction, the rate of forward reaction equals to the rate of reverse reaction when the reaction achieve equilibrium. This point we can interpret it also in the form of graph. Now we have a graph of rate against time. As the reaction proceeds, as the time increases, the reactants A and B will react together and start losing itself. So the rate of losing the reactants will decrease. At the same point, we are forming the products. So the product of the rate of producing C and D is increased. When the system reaches an equilibrium, we can see the rate of forward reaction is equals to the rate of the reverse reaction. So we can say at this point, at TA, the reaction had achieved equilibrium. How? How to prove it? By looking at the same rate of forward reaction and the reverse reaction. Same, the forward reaction equals to the reverse reaction. So, this is a summary to interpret the equilibrium reaction. A system is at equilibrium when we can interpret the concentration of the reactants and product in a form of graph, and we can interpret the rate of the reaction in a form of graph. So once again, the concentration of the reactants and product become constant when the equilibrium achieved, while the rate of the forward and the reverse direction or reaction in the chemical reaction become equal once the equilibrium achieved.
Say two people are walking down the street and they bump into each other. They'll just shake it off and walk on. Sometimes that happens with molecules too. They just bounce off each other and that's that. But what if two people were to bump into each other and during that collision, one person's arm got severed and reattached to the other person's face? Now that sounds really weird, but it's similar to one of the many ways that molecules can react with each other. Two molecules can join and become one. One can split apart and become two. Molecules can switch parts. All these changes are chemical reactions, and we can see them happening around us. For example, when fireworks explode, or iron rusts, or milk goes bad, or people are born, grow old, die, and then decompose. But chemical reactions don't just happen willy-nilly. Everything has to be right. First, the molecules have to hit each other in the right orientation. And second, they have to hit each other hard enough, in other words, with enough energy. Now, you're probably thinking that a reaction just happens in one direction and that's it. Sometimes that's true. For example, things can't unburn or unexplode. But most reactions can happen in both directions, forward and reverse. There's no reason that our face arm guy can't bump into armless girl, reattaching that arm back to its original socket. Now let's zoom out a bit. Now let's say that you've got 1,000 people on the street, and all of them start with their limbs normally attached. At the beginning, every collision is a chance for person A to transfer an arm to person B's face. And so at the beginning, more and more people end up with arms attached to their faces or arms missing. But as the number of people with arm faces and missing arms grows, collisions between those people become more likely. And when they bump into each other, guess what? Normal appendage people are reproduced. Now, the number of limb transfers per second forward will start high and then fall, and the number of limb transfers per second backward will start at 0 and then rise. Eventually, they'll meet, they'll be the same. And when that happens, the number of people in each state stops changing, even though people are still bumping into each other and exchanging limbs. Now, how many people do you think there are in each state? Half and half, right? No. Well, maybe. It depends. It could be 50-50, but it could be 60-40 or 15-85 or anything. We chemists have to get our little gloved hands dirty. We're in a lab, so not really dirty, to figure out what the actual distribution of molecules is. Even though each of these limb transfers is a pretty dramatic event for the people involved, if we zoom out, we see population numbers that don't change. We call this nirvana equilibrium, and it doesn't just happen with chemical reactions. Things like gene pools and highway traffic show the same pattern. It looks pretty still from 30,000 feet, but there is lots of crazy stuff happening on the ground. You just need to zoom in to see it.